Welcome to part 1b of our lecture on learning from graphs. So what we will be doing in this part B is talking about embeddings. So basically what embeddings are is low dimensional representations of objects. That's very general. So let's decompose this a bit. So what does low dimension actually mean? So low dimension means much lower as the original size. So let's say if you have an embedding of an image, well, it should not be as big as the number of pixels in the image, but it should be much smaller. It's a representation, so it means there is some meaning to it, right? So it really represents, it corresponds to something, it corresponds to an object in the real world. Objects in the real world could be all kinds of things. So it could be words, could be sentences, could be images, could be audio, or could be graphs, as we will see later on. Now, you already saw several examples of embeddings. We didn't always really call them like that, but they actually are embeddings. So if we first look at the example there on the left, then you will see that this here, so there was an input image, then we had this this filters of the convolutional layer, and we have an output here, right? And now this output is a representation of that image. It has a lower dimension, so it is basically an embedding. We also saw things like variational autoencoders or other generative models, and so they also had this space in which the points were this distribution basically, and also points in there are basically embeddings corresponding to a real-world image in this case. Now, a very nice property of some embedded spaces is that they also have a useful structure. Right? So they have a structure which you can navigate, and navigating in certain directions in that embedded space has a certain meaning. And what it also means is if you navigate in a certain direction, that certain features of the object would actually change. So in this case, in the images, if you navigate in a certain direction in the space, basically you move your image from a person who is smiling to a person who is not smiling. You would move from a female gender to a male gender if you follow a certain direction. If this is the case, then it's said that these features are basically disentangled in the embedding space. So they basically sort of separated from each other, and certain directions correspond to certain semantic features in your objects, in this case in the image. Now, besides images, we can also have embeddings of words, right? So before we just have images, we can make small representation. Now for words, we can do the same. So the thing is that if you want to work with words in machine learning setting, you can do things like a one-hot encoding, meaning that you have a big factor, you put a 1 at the index of that certain word. Problem is that this has all kind of problems, which you should watch the videos basically which we had on the topic. But for creating embeddings of words, there is one thing which is usually central, and that is what is called the distributional hypothesis. So there is this famous quote from Firth, which basically said that you shall know a word by the company it keeps. A bit of a more modern version is that, so if units of text, meaning words or maybe a little bit bigger things, have similar vectors in a text frequency matrix, then they tend to have similar meaning. So to give an example, if you have a word like cat, it occurs often in the context of the word animal. And the same holds for the word dog and fish, right? So they often occur in the context of the word animal. But if the word loudspeaker, well, it hardly ever occurs together with animal. So it basically means you can conclude that the word cat, dog, and fish are similar to each other just because they appear in the context of another word. You can know that loudspeaker is a different word because it does not co-occur with the word animal in the way dog, fish, and cat would do. So with this information, you can start making embeddings of things. So, and the way you do that is by creating a vector representation for each of these words. This could include information about a co-occurrence with words, for example, but in general, we can also train these embeddings, and then I suggest you watch the lecture which we had on word2vec. Okay, so now we have had images, we've had words, and also here, just as with images, we have a notion of navigating through space. Right? So This example is not real realistic, but still it illustrates the idea. So if we have a certain concept, like for example, king, then it would, if you navigate a certain direction in space, you would end up with a representation for the word man. And very similarly, if you follow a similar direction from queen, you would end up with the embedding of the word woman. And this way you could also have it, let's say, from capitals to countries, or for example, change certain grammatical forms of words and so on. Okay, so we have had images, we have had words. Let's now look at graphs. Now, the first thing which we have to ask ourselves is, it's all very nice. The reason we do this for words and images is that we want to use them in machine learning. So what if we should first look at, before we start talking about embedding graphs, is why do we even want to use them as an input to machine learning? It's basically things which you want to do is, for example, we want to do a classification, regression, or clustering of nodes in the graph, edges in the graph, or the complete graph. To give an example, so we might have, for example, let's say we are Amazon and we have our product graph. But now for some of the products in the graph, we do actually not really know what these products are. Okay, so you might have seen a lot of errors when you're browsing this kind of web stores. And so what we want to do is we want to classify nodes for which certain labels are missing. And then, we basically need to feed that graph information into classifier, or nodes into classifier. For a whole graph, well, a good example there would be, we want to take a graph of a molecule, and we want to detect whether this is poisonous or not. So that's basically a binary classification. It's either poisonous or it's not. With a regression, again, we could then, for example, say what is the level of toxicity of this molecule. Okay, other cases, for example, recommender systems. So who likes what, right? So for example, we are again Amazon. We have sold you a washing machine. And now we want to recommend you the next products which you might want to buy. So again, maybe it's a certain washing liquid, and that is something which is not obvious because these products are not similar at all, but in the knowledge graph, they're connected with each other. And next case is document modeling. So in document modeling, basically you would have, you have documents, text documents typically, and now some of the entities you're linking from that text to your knowledge graph, and then your knowledge graph is helping you decide that two documents are similar. Okay, so it basically uses these concepts. It's also very much related to the last point in this graph, which is about linking text and other semi-structured knowledge to graphs, for example, information from tables and so on. One more which is mentioned here is the alignment of graphs. For example, you would have two different graphs, and you want to tell whether, for example, two nodes, a node here and a node there, are actually similar to each other. So you want to align those graphs in a certain way. Could be used, for example, if you have two molecules in, for example, a protein and something which can bind on that protein to see where that exactly could match. And then a very general set of tasks is link prediction, error detection. It means basically you have your knowledge graph, and a knowledge graph, like the examples which you saw before, let's say that you're talking about the Google knowledge graph, it's crawled from web information. So this graph will always contain mistakes. It will contain links, or there will be links which are missing, there will be links which are just wrong, and so on. And a general task is then basically to do a link prediction, so refind links which are missing, and then remove links which are just wrong. So all of these tasks could be solved with machine learning in case we can get that knowledge graph into our machine learning models. So that's what we want to do next. In part 2, which will then be on graph embedding techniques.